Thank you. Thanks for the introduction. Thanks for coming to everybody. As you've probably guessed by the title of the presentation, I'm going to introduce you to the problem of detecting whether one text is written by a person or generated with a GPT. I won't ask you to raise your hands because I know most of you have used GPTs, maybe to generate some text or just to answer a question that the good old Google failed. And there is nothing wrong with that. I do it too. However, there is one fact that is a bit concerning and can cause some problems. The fact is that we as people aren't good at recognizing such text. There are researches that show that we have a chance of around 50-50, so we are as good as a coin when we detect such text. And this can, of course, cause some problems in the future. For example, back when I was in high school, I hated writing essays. So what I did was to read essays of my friends or read some analysis on the internet, and I built some kind of an essay on my own. However, nowadays, this can be done with only 2 clicks in ChatGPT, and it will generate a well enough written essay which can do the job. However, in the long term, this can cause a lot of problems in the educational sphere, for example, and people can exploit this feature of ChatGPT. Furthermore, we are already becoming witnesses of the problem of the internet that is full of information written by GPTs, and I doubt anybody wants to have web pages written with artificial content. And last but not least, GPTs are not always correct. Sometimes they make mistakes, and on a bigger scale, they can actually spread a lot of misinformation. So my goal here is to introduce you to 2 different solutions for detecting whether one text is written by a person or generated with a GPT. The first solution is fine-tuning of an existing distilled model, which already understands text quite well, while the second one is actually using GPTs in order to detect whether one text is written by a person or generated with a GPT. At the end of the presentation, I'll show you a brief demo of the second approach, which will be available to download and try at home. Before I start, I just want to go through the next slide, which is a bit tedious, I know, a bit boring, because it's a theory on how neural networks work. But I just want to make sure that we're all on the same page, so you can understand the approaches. So a neural network, simply said, is some kind of an input in the beginning on the bottom, that is a set of numbers. So text can actually be represented as numbers. And these numbers are simply multiplied by some sort of weights or parameters that are hidden behind the first orange edges on the bottom. After some operations, after multiplication, we get this middle or hidden layer, which is, again, a set of numbers. And we can similarly multiply it again by a different set of parameters, and in the end we get the output as either true or false, in our case, whether a text is written by a person or generated with GPT. I hope that most of the people here have watched Fast and Furious, and why I'm saying it is because there is actually a correlation on the cars there and how distilled fine-tuning works. If you haven't, it's a movie about some cars, racing, Vin Diesel and his family. So the thing is that these cars that the guys race with were actually once manufactured as normal cars. But in order to make them faster, they just changed their engines, changed some parts in them, and the goal is to make them specific for one task, which is racing. So similar approach conceptually can be applied to neural networks. What we can do is take a base model that already understands text quite well, so similar to the car manufactured somewhere, and we can modify it in order to make it specific for one job, which is detecting whether one text is written by a person or generated with GPT. And in order to do that, we have to feed through the neural network some texts that are already classified as such. So we have a data set of some texts that are written by people and some texts that are written by GPTs. And in order to do that, we need some kind of a data set with text. A suitable one is the M4 dataset, which has some Bulgarian participants, actually. And it consists of a bunch of text written by people and then rephrased by different GPTs. And when we take, for example, 2,000 human text and 2,000 ChatGPT text, we can feed them through the neural network, and it will start recognizing whether one text is written by a person or generated by ChatGPT. And in order to test this, we need another set of 1,000 human text and 1,000 ChatGPT text to test the whole model with text that it hasn't seen during the training period. So when this is done, you can get an accuracy of around 99%, which is incredible. So out of 2,000 texts, we have only 20 which are mistaken. However, it turns out that it's very easy to break such a model. And the way to break it is by simply testing it with some texts that are not from ChatGPT, but generated with another one, for example, BloomZ. The reason this happens is because the model that we trained actually overfits a lot on the types of text and the GPTs that were generated, that were used to generate the text, and it can't recognize text from different GPTs. On top of that, it turns out that too many GPT texts are actually classified as humans, and the reason is the same. It can only recognize ChatGPT text. On top of that, it turns out that not only the GPTs that are used to generate are important, but also the types of text have impact on such a model. For example, if we trained our model on some text coming from Reddit, and we tested with some text that are, for example, sport articles or law documents, whatever you like, it will actually, again, fail. Luckily, there are other approaches that use some linguistic features of the text, that use some changes on the text and comparison between them, but maybe the most suitable ones for our task are the ones that use probabilities. And there is actually a very good reason why probabilities make sense in this scenario. The reason is that GPTs under the hood actually use probabilities in order to generate the text. For example, if a GPT is generating some kind of a text, it will compute the probabilities for each word it knows in order to select it and put it as the next word. And it goes on and goes on until the text is finished. So here we have an example of the context "I love eating," and the GPT would yield a probability of around 0.09 for pizza, which is quite high, because pizza is common in the context of "I love eating." However, the word "going" doesn't really make any sense. It's not grammatically correct. So the GPT will actually put a low probability, and there is a very little chance that it will select it as the next word. So not only that, but also we can use GPTs to put some text into them that somebody has written. Doesn't matter if it's us, if it's another GPT. And the GPT will actually compute the probabilities of these words as if the GPT was to generate the text. So I can write a sentence, "I love eating liver," and I can ask a GPT to give me the probabilities that it thinks are suitable for the said sentence. And by doing so, people actually observed that the human texts usually yield lower probability than the texts that are coming from GPTs. And there is a good reason why this happens. The reason is that we as people are quite different from each other, use different vocabularies, and express ourselves in various ways, whereas the GPTs are almost trained on the same datasets. They share similar architectures, and their job is actually to maximize this probability in order to generate texts that make sense to us people. So all this said sounds like a good enough foundation for a model that can detect such texts. The only thing we need is to find a number that sits between the human probabilities and the GPT probabilities, and everything above it will be detected as GPT, and everything below it will be classified as human. But again, there is one problem, and the problem is the prompt. We all know that the prompt has actually a very big impact on what is generated by the GPT. For example, if I ask ChatGPT or any other GPT to write a sentence about a fictional character that eats cars, it will probably generate something like "I love eating cars," which, if we take out of the context of the prompt, it makes not a lot of sense. And another GPT will calculate the probability of cars, of the word "cars," as very low, because it doesn't have the context of the prompt. And when we detect texts, we don't have the prompt, we have the text as it is. So people that want to bypass such detectors can easily do it by using some prompts that are specifically engineered for this case. And in order to bypass this problem, we have the binoculars approach. So the binoculars approach doesn't use only one GPT to compute the probabilities, but it adds a second one, which kind of communicates with the first one, and they work in collaboration in order to make a more stable decision on whether the text is written by a person or generated with a GPT. The score, or the metric that is used in the binoculars approach, is highly correlated to probabilities, but instead of calculating only a single probability, it has a denominator of cross-perplexity. So the metric, simply said, measures how surprising is one text to a GPT when we ask about its predictions. And in other words said, if we have high perplexity, which probably means that the text is written by a person because it's surprising to a GPT, this means that we had lower probabilities when the GPT yielded the probabilities for each word. And the opposite is also, of course, valid. So on top here, in the numerator, we have the metric perplexity, which is simply a calculation on the predictions of the first GPT to the text itself. So it measures how well the GPT generates or predicts this text, while in the denominator we have cross-perplexity, which is a very similar metric. We will see a bit in the demo. But instead of comparing the GPT to the text, it actually compares the understanding of the text from both GPTs. And to put it a bit simply, here in numbers, for example, if we have some kind of a human text, it will have perplexity of around 2.4 in the numerator, while in the denominator, we'll have a number of around 2.6, for example. Then, when we do this calculation, we get a score of 0.92, which is above a threshold, which we'll see in a bit. So thus, we will classify this text as human. On the other hand, if we have a GPT text that was generated by a machine, we'll have a perplexity of 1.43 and denominator of 1.96, which as a result is 0.72, which is way below the threshold that I mentioned, and the text will be classified as generated by a GPT. So in order to verify all this, we can run all the text in this dataset that I mentioned that consists of text from different GPTs, from various sources and on various topics. And when we do this, we get a result of 78%, which I know isn't that incredible. However, if we think a bit more about it, it's way more stable because it doesn't require any fine-tuning. It doesn't have to read any text, so it works in the more general case, although it's not perfect, of course. And on top of that, it actually very rarely classifies human text as GPTs, so there isn't really any discrimination whatsoever. So, as I promised, I'm going to show you a quick demo of the second approach. For the purpose of the demo, I'm using the Google Collaboratory environment. All right. In case you haven't seen the Google Colab environment, I'm highly recommending it because it actually gives you a free GPU, which you can use in order to load the GPTs. In order to do that, you can click here and change the runtime type, then select the GPU, click Save, and after connecting to the runtime by clicking this button, you have a GPU, which you can use for free for a couple of hours every day. Other thing to mention is the code itself. As you can see, it's not purely Python code. It's actually using the format of Jupyter Notebooks, which consists of some Python code and some markdown blocks in which you can add text or you can add images, visualizations, different graphs. It's upon you, so it's some kind of a mixture between code and text, which can work as documentation. Here on the first line, we can see some libraries that we have to install because they don't come out of the box from Google Collaboratory, and we need these libraries in order to load the GPTs from the Hugging Face platform. In order to do so, you need registration on Hugging Face in case you have, if you don't have. But it's again totally for free. You just need a token, which I'll show you how to use in a bit. Then we, of course, have some imports. Some of them are to the libraries that I mentioned. Some of them are pure generic Python imports. And one of the most important ones is actually the PyTorch library we see here, which we use in order to calculate the perplexity and the cross-perplexity. Next, we have the two lines that are maybe the most important ones, the names of the GPTs that we're going to use in order to make the detections. Here, I've used Mistral, and the two GPTs are actually very similar to each other, and that's the way it should be. As the more similar they are, the better results you can get. And I've selected the Mistral GPTs because I can guarantee that they load correctly here in the environment and there is enough space for them. However, you can experiment with any other two GPTs that don't require that much memory in the GPU that is provided by Google. Afterwards, we have the threshold that I mentioned a bit before, and obviously it's mathematically calculated. It's not something that somebody just thought about it. It was calculated by doing a lot of experiments, and usually it was calculated with a different set of GPTs, but it is stated that it's stable enough, so it can be used actually with a different set of GPTs from the ones that were used when it was calculated. Then we have a block of code with the two functions that calculate the perplexity and the cross-perplexity, or the numerator and the denominator in our calculation. I won't go through all of the things here, but I want to mention that the function that is used is actually the same. The only difference is the parameters. And in the first case, as I said, we compare the predictions of the GPT to the text itself, while in the second case, we compare the predictions of the first GPT to the predictions of the second GPT, which works like a normalization factor on the thoughts of the first one. And then we have a short but actually very important line. This one makes sure that the GPTs actually load correctly in the memory. Otherwise, they take too much memory and you run out of it. So without this line, you won't be able to actually load the GPTs in this specific Google Cloud environment. If you have a powerful computer with a GPU, then you can pass this line. But what it does is simply lowering the performance of the GPT a bit, but actually the memory that we gain is quite a lot, so it's worth it. Then, as I promised, I'm going to show you the token here, which you need to get from Hugging Face. You can pass it to a config or here in the function code directly, and you can store it here in the secrets that are provided by Google Colab. I don't have internet yet, but you can add new secret entity to save it for you. Then we are to the heart of the whole detector, which is this class. In its constructor, we can see that we load the two GPTs. I lost my mouse just a bit. Okay, there it is. So in the constructor, we load the two GPTs by passing their names, which we stated a bit above in the constants. And we also have to pass the configs that we built a bit in the blocks above. Afterwards, we have to initialize the tokenizer, which job is to be used here in the tokenize function in order to split the text into words. So when we pass a text to GPT in order to calculate the probabilities that I've been discussing, we have to actually pass it word by word, or more specifically token by token. A token is not always a word as we understand them. Sometimes it can be actually part of a word or even just a symbol. But that's how GPTs actually understand the text. So after we have the text tokenized into different parts, we pass these parts to the to GPTs, and they'll give us their predictions of the text. Then we go to the last function, which is some kind of a driver function, and basically calls all the other functions in a specific order. And in the end, we need to divide the perplexity and the cross-perplexity, which were calculated in the same function. As a result, we get one number for one text, which we can compare to the threshold. If the number is above the threshold, then it means that it is written by a person because it's surprising. The text is surprising to the GPTs. If not, the number is lower than the threshold. It means that it was generated with a GPT. In order to test this, you just have to initialize this detector class and pass some text to the compute score function, which will return the score for each text that you've passed. I just want to mention here that if you use too large texts that are too long or too many texts, you might run out of memory in the environment. So keep them a bit shorter. For example, something around 300 or 400 words works fine. I've just given these as an example, and they're shorter. Yeah, as I said, it returns the two scores for the two texts that I've passed, and you can compare them to the threshold. If you're just curious more about the topic, you can read more about the dataset and this approach that I showed here in the demo from these links. And just let me get back to the presentation. All right. So in order to download this notebook, you can just scan the QR code or put the link in your browser, and you have to make one copy on your drive, for example, because it's read-only, so you won't be able to make any changes. Then you can connect to it, run it, test it with some text, and do whatever you like with it. So having said all that, without a shadow of a doubt, there isn't a perfect solution that works in all the cases and that can detect all the text in the world. However, I hope that I managed to ignite some kind of a spark in you, because who knows, the next breakthrough might be by you. Thank you.
Thank you very much. We have time for a few questions. So first one.
First of all, great presentation. Really got my interest. So two quick questions, actually. First one is about the temperature. Does it somehow affect the results? And the second question is a little bit more tricky. Could we actually reverse the algorithm, knowing how it works, and having GPT-generated text humanized and being undetectable?
Yeah, okay. So about the first question for the temperature, I won't go into a lot of details, but yes, it actually has impact. So when we compute the predictions from the two GPTs, we can add temperature in order to make them a bit better or worse, depends on the temperature. So it has big impact. I haven't used it here in order to make it a bit more simple, but yes, your note is correct that the temperature has a lot of impact on the predictions. About a second question, it really depends on the GPTs that generate the text and what prompts you add to them. The prompts that were used in this dataset that I mentioned are tricky enough, I think, because I've seen some of them, because they state to generate text that is, for example, written by a 5-year-old or written by a foreigner that doesn't speak a lot of English. So the texts that were initially written by people were rephrased in such ways. But yeah, probably another GPT, if it appears, it might actually break this whole method too. Yeah, it's not a perfect solution at all.
Okay, do we have any other questions?
Thank you very much for the talk. One thing I was curious, you mentioned for the binocular approach that it tends to be fair and to not behave bias towards the input from people, so to misclassify something that people wrote as AI-generated text. So how is that achieved? Because I remember in the summer there was this article that they did statistical analysis on the generated automatic code and text and identified words like delve, augment, etc., which were strong indicators. And someone posted it, and there was a scandal because a specific location of people that are not United States or UK, they're using that, and basically it was misrepresented that it was AI generated based on what they're writing. So is that this somehow addressed outside of the general way LLMs work? Or?
Yeah, so the metric that is used is score of division between perplexity and cross-perplexity, because usually perplexity is good enough, but as you mentioned, if the GPT that generates the text has generated something that has a bit more tricky words, like you mentioned, like augmented or whatever the words are. The cross perplexity measures how surprising is this text to the first GPT. So on intuitive level, it's a bit tricky, but the thing is that the GPTs are closer to each other than they are to people. So by doing this calculation, they can actually distinguish a bit better whether the text is written by a person or generated with a GPT.